In this video, we're going to look at Cambridge International AS and A-Level Mathematics 9709, Probability and Statistics 1, Paper 5-2 from May-June 2025. Let's start with question 1. Rachel has 3 coins. The first coin is biased, so that the probability of obtaining a head when it is thrown is 1/3. The second coin is biased, so that the probability of obtaining a head when it is thrown is 1/4. The third coin is fair. Rachel throws 3 coins at the same time. The random variable x is the number of tails that she obtains. Draw up a probability distribution table for x. X is the number of tails that Rachel obtains. So let's start with our table. In our top row, we have x, and our bottom row, we say the probability that x is equal to x. Rachel has 3 coins, and we need to consider the number of tails from those coins. We could have no tails at all, 1 tail, 2 tails, or tails from all 3 coins. To find the probability for 0, 1, 2, and 3 tails, it is always easiest to start with the most basic combinations. And in this case, that is no tails at all or 3 tails. So let's start with no tails. Let's make some space. Before we do this, let's make some quick notes about the probabilities for each coin in terms of heads and tails. The question tells us that the first coin is biased, and the probability of obtaining a head is 1/3. So up here I can say for coin 1, probability of it landing on a head is 1/3. If the coin lands on tails, that means it does not land on heads. So the probability for tails is the complement, which in this case has to be 2/3. The second coin is also biased. The probability of it landing on a head is 1/4. So here I can say for coin 2, probability of heads is 1/4. So for the coin to land on tails, must be 3/4. Coin 3 is fair. That means there is equal chance of it landing on a head or on a tail. So probability of heads has to be 1/2, and for tails as well. If all 3 of Rachel's coins do not land on tails, that means that all 3 land on heads. So we get heads from the first coin, and heads from the second, and heads from the third. Because we have a head and a head and a head, we need to multiply the respective probabilities together. Probability of a head from coin 1, 1/3, and probability of heads from coin 2, 1/4, and probability of heads from coin 3, 1/2. Multiply these, and we get 1/24. This is the probability of no tails. So I'm going to put this into my table. Under 0, I say 1/24. Now let's look at the probability of 3 tails. That's all 3 coins landing on tails. So tails from coin 1, and tail from coin 2, and tail from coin 3. Tail from coin 1 is 2/3, so 2/3, and a tail from coin 2, 3/4, and tail from coin 3, 1/2. Let's multiply these together. 2 and 3 gives me 6, over 24. Now, when working with distribution tables, there's a high chance you may need to add your fractions together. And it's easier to do this when you have the same denominator in each fraction. So in this case, I'm going to leave my fraction as 6 over 24. But if you want to, you can simplify it to 1 over 4. Let's put this into my table as well. 6 over 24. Now I need the probability of one tail or two tails. Let's start with one tail. I'm going to make some space. If I get one tail out of the 3 coins, that means I get a head from the other 2. So I can get a tail from coin 1, head from coin 2, and head from coin 3. Or I can get head from coin 1, tails from coin 2, and heads from coin 3. Or I can get heads from coin 1, heads from coin 2, and a tail from coin 3. Let's start with a tail from coin 1. Probability of a tail from coin 1, 2 over 3. Let's say 2 over 3. Heads from coin 2, 1 over 4. So we multiply by 1 over 4. Heads from coin 3, 1 over 2. Let's see what happens if my tail is from coin 2. This means I get heads from coin 1, so probability 1 over 3, and tails from coin 2, 3 over 4, and heads from coin 3, 1 over 2. For the last option, heads from coin 1, 1 over 3, and heads from coin 2, 1 over 4, and tails from coin 3, 1 over 2. Now we can quickly multiply these together. I get 2 out of 24 if I get tails first. If I get tails second, I have 3 over 24. If I get tails third, probability is 1 over 24. But remember, I could get tails first, or tails second, or a tail third, which means we need to add these together. 2 plus 3 is 5, plus 1 is 6. The probability of getting one tail is 6 over 24. And I can put this into my table as well. Now, you can use a similar method to find the probability of two tails. But remember that in a distribution table, the sum of the probabilities will always be equal to 1. So now that we have 3 probabilities, we can create a sum to find the probability of two tails. Let's add these together quickly. 6 plus 6 is 12, plus 1 is 13. So right now I have 13 over 24. I'm going to write 1 as a fraction over 24. I can say 24 over 24 minus 13 over 24, and I'm left with 11 over 24. This is the probability of two tails, and I can fill this in to my table over here. In Milford, 70% of the residents own a bicycle. A random sample of 160 residents is selected. Use a suitable approximation to find the probability that more than 120 of these residents own a bicycle. When you see approximation, we know that we have to convert binomial distribution to normal distribution. So let's start with our binomial. When working with binomial distribution, we need a value for n, for p, and for q. N is the random sample, so in this case, 160. I'm going to make a note of this over here, 160. P is our probability, in this case, 70%. Let's make it a decimal, and we see that P is equal to 0,7. Q is the complement, so Q is equal to 0,3. we are converting to normal distribution. So we're going to use the formula Z is equal to X minus mu over standard deviation. To find the value of mu, we use NP. N is 160 and P is 0.7. So I can say 160 multiplied by 0.7 is equal to 112. This is my value for mu, 112. For the standard deviation, I use NPQ under a square root. I already know that NP is 112. So let's multiply by Q, 0.3 is equal to 168 over 5 square root, and we get 2 root 210 over 5. This is a very complicated root with a fraction, so I'm going to square this back to our original value. And I'm going to write our standard deviation as 168 over 5 under a square root. Now I have mu, I have sigma, but I need x. The question tells us to find the probability that more than 120 of these residents. 120 is our x value, but remember that you need to manipulate this value. If we are looking for probability more than, we add 0.5 to this value. So in this case, x is equal to 120.5. Now I can put these values into the formula. I'm going to say z is equal to 120.5 minus mu, 112 over 168 over 5, all under a square root. Now I can take my calculator. Let's say 120.5 minus 112 divided by the square root of 168 over 5 is equal to 1,4663. We're looking for a z-score, so let's write it as z is equal to 1,466. Now to find my probability, let's look at my table. I have 1,4, so we start here. 1,46, so we move to this column over here, down to the bottom, and I get 0,9279. I'm going to write this over here. 0,9279. But my z-score is 1,466. So I need to add 6 over here. Go down to the bottom, and I see that I need to add 8 to my probability. So plus 8 over here, and I get 0,9287. So let's go back to our answer, and I can say the probability is equal to 0,9287. But remember, when working with normal distribution, probability you get from your table is always the probability that x is smaller than a value, but we want the probability that it is greater. So to find our final answer, we say 1 minus 0,9287. Take my calculator. 1 minus 0,9287 is equal to 0,0713. 0,0713. And this is my answer. Question 3 says a bag contains 4 blue marbles and 12 red marbles. One marble is selected at random from the bag. If this marble is blue, it is replaced in the bag, but if it is red, it is not replaced. A second marble is now selected from the bag. Part A, find the probability that both marbles selected are the same color. Let's start here. If both marbles are the same color, we'll get a blue marble first and a blue marble second, or we could get a red marble first and a red marble second. The question tells us there are 4 blue marbles and 12 red. So over here, I can just say 4 blue marbles and 12 red, which gives us a total of 16 marbles. If a blue marble is removed from the bag, it is then replaced. So the first marble does not impact the probability of the second. So if my first marble is blue, probability is 4 over 16. And a second blue marble, so we're going to multiply, again 4 over 16. Now let's look at our red marbles. We have 12 red marbles out of a total of 16. So if our first marble is red, probability is 12 out of 16. But the question tells us if it is red, it is not replaced, which means once this marble is removed, we now have 11 red marbles out of a total of 15. So probability the second marble is red has to be 11 over 15. We need to find the probability that both marbles selected are the same color. This means they could both be blue or they could both be red. So we need to add these two sets of probabilities together. So now I can take my calculator. I can say 4 over 16 multiplied by 4 over 16 plus 12 over 16 multiplied by 11 over 15 is equal to 49 over 80. This is the probability that both marbles are the same color. Now let's move on to part B. Find the probability the first marble is blue given the second marble is red. The word given shows us we are working with conditional probability. When working with conditional probability, we use the formula probability of B given A is equal to probability of A and B over the probability of A. In this case, B is that the first marble is blue. So I'm going to say probability that the first marble is blue given the second marble is red. Second marble is red is now equal to probability the first marble is blue and the second marble's red over the probability that the second marble is red. Let's start with the probability that the first marble is blue and the second marble is red. The only way that this can happen is if we draw a blue marble first and a red marble second. We know the probability of drawing blue marble first, 4 over 16, and drawing a red marble second has to be 12 over 16. Multiply these together, take my calculator, 4 over 16 multiplied by 12 over 16 is equal to 3 over 16. This is the probability that the first marble is blue and the second marble is red. Now I need to find the probability that the second marble is red. For this to happen, my blue marble is first, followed by a red marble, or I can have a red marble first and a red marble second. We already know that the probability of blue first and red second is 3 over 16. I can put this over here. Or, so we're going to add 2 red marbles. A red marble first, 12 over 16. And we saw this in part A. If the second marble is also red, probability is 11 over 15. Now I can take my calculator. I can say 3 over 16 plus 12 over 16 multiplied by 11 over 15 is equal to 59 over 80. 59 over 80. Now I can fill these fractions into my formula. So I can say the probability that the first marble is blue, given the second marble is red, is equal to probability the first marble is blue and the second marble is red, 3 over 16, over probability the second marble is red, 59 over 80. Let's put this into my calculator. 3 over 16 over 59 over 80 is equal to 15 over 59. 15 over 59. Vehicles approaching a certain road juncture from Bromley must either go left, right, or straight on. Over time, it is known that 30% turn left, 25% turn right, and 45% go straight on. The driver of each vehicle chooses a direction independently of all other drivers. Part A says find the probability the next 3 vehicles approaching this juncture from Bromley all go in different directions. If vehicles are going in different directions, one will go left, one will go right, and one will go straight. Let's start by making some notes of these respective probabilities. 30% turn left, so the probability of left has to be 0.3. 25% turn right, so the probability of right is 0.25. 45% go straight, which means the probability of straight is 0.45. All 3 vehicles go in different directions. So let's look at the different combinations we could have. The first vehicle could go left, the second one straight, and the third one right. Or the first one left, the second one right, and the third vehicle straight. Maybe the first vehicle goes straight, the second one right, and the third one left. Or first one straight, the second one left, and the third one right. What if the first vehicle goes right, the second one goes left, and the third one goes straight? Or the first one goes right, the second one goes straight, and the third one goes left? There are 3 possible combinations we need to look at. So let's look at the first one. The first vehicle goes left. Probability of left is 0.3. And the second vehicle goes straight. Probability 0.45. And the third vehicle goes right. Multiply, probability of 0.25. Now, in all of these combinations, we have a vehicle going left and right and straight for all 6 of these. So to make this easier, all we need to do is multiply all of this by 6. So now I can take my calculator. I can say 0.3 multiplied by 0.45 multiplied by 0.25 multiplied by 6 is equal to, turn into a decimal, 0.2025. This is the probability that all 3 vehicles go in different directions. Now we can move on to part B. Find the probability from vehicles approaching this junction from Bromley today that the first vehicle to go left is before the 9th vehicle. When you see the word before, fewer, less than, smaller than, we know that we are working with either binomial distribution or geometric distribution. In this question, we are looking at before the 9th vehicle, but we do not have a total number of vehicles. So this is a geometric distribution. So I can say the probability that x is smaller than 9. when working with geometric distribution for something smaller than or before, we can use the formula P, probability that X is smaller than or equal to R, which is equal to 1 minus Q with an exponent of R. But please be careful here. We are looking at X values smaller than 9, but for the formula, it is smaller than or equal to R. So in this case, smaller than 9 means that X has to be smaller than or equal to 8. This is our R value. Please learn this formula. It is not in your formula sheet. Our R value is 8, but we still need a value for Q. And remember that Q is the probability that something does not happen. In this question, we are looking at vehicles that go left. And we know that 30% turn left. So the probability P is 0,3. This means the complement Q has to be 0,7. So if the first vehicle to go left is before the 9th vehicle, we can say X is smaller than or equal to 8 is equal to 1 minus Q 0,7 with an exponent of 8. Take my calculator. 1 minus 0,7 with an exponent of 8 is equal to 0,9423. I'm going to round off to 3 decimal places and get an answer of 0,942. And now we can move on to part C. Find the probability that the vehicles approaching this junction from Bromley today, the second vehicle to go left is the 7th. Statistics is realistic, so let's draw a quick diagram. I'm looking at 7 vehicles. 1, 2, 3, 4, 5, 6, and 7. The 7th vehicle goes left. I know that. This is the second vehicle to go left, which means out of the first 6 vehicles, 1 has to go left, but the other 5 will not go left. We know the probability of left is 0,3, so the probability of not going left, Q value, is 0,7. Now we can find the probability the 7th vehicle is the second one turning left. The 7th vehicle turns left, so let's start there. Probability of left, 0,3. And the first 6 vehicles also need directions. Of these 6, 1 goes left, so we can say and 0,3 for the one car that goes left. And 5 don't. We're going to use the complement 0,7. 5 cars don't go left. So we're going to multiply 0,7 by itself 5 times. To make this easier, we just give it an exponent of 5. Now we know that the 7th vehicle is the second vehicle to turn left, and that 1 vehicle in the first 6 also turns left, but we don't know, is it the first or the second or the third or the 5th or the 6th. So to make this easier, we need to account for all of these values. So we multiply our equation by 6. Now I can take my calculator. I can say 0,3 multiplied by 0,3 multiplied by 0,7 with an exponent of 5 multiplied by 6 is equal to 0,907. Let's round off to 4 significant figures and get an answer of 0,908. The times taken, T minutes, by 300 students to travel to Hollerton College are recorded. The results are summarized in the table below. Part A says on the grid, draw a cumulative frequency graph to illustrate this information. Now, always start by creating your intervals on your X and Y axes. Time runs along your X axis and your cumulative frequency runs along your Y axis. When planning your intervals, use your space, use all of your space. Don't try and squeeze your graphs into the bottom corner. In this graph, we have 1, 2, 3, 4, 5, 6 blocks. And we need to consider times from 0 to 90. 90 divided by 6 is 15. So I'm going to use intervals of 15 along my x-axis. I don't have the space to squeeze this in here, but in your exam, you should write time along your x-axis just so your marker knows what you are working with. Cumulative frequency runs along the y-axis. We have 1, 2, 3, 4, 5, 6, 7, 8 blocks. Let's take my calculator. Cumulative frequency we have from 0 to 300. 300 divided by 8 is equal to 37,5. So I'm going to create intervals of 40 from 0 to 320. Always make a note along the y-axis that this is the cumulative frequency. And now we can start plotting our points. The x-coordinate of each point takes on the value in the block. It's always the highest value. So for our first point, it's going to have an x-coordinate of 10 and a y-coordinate of 34. We can plot this point over here. Then we have time of 20 and cumulative frequency of 86. Let's make a note of that. And I can plot this point over here. I am making notes of the coordinates of each point. And I find that it's not a bad idea, just so your marker can see what you're attempting to do. But if you don't have enough time, don't worry about these coordinates. But if you can, try and do this too. For our third point, we have a time of 30 and our cumulative frequency is 142. Make a note of this. And I can plot this over here. Then I have a time of 40 and cumulative frequency of 208. Let's plot that point. Then time of 60, cumulative frequency of 265. Let's plot that point. And finally, a time of 90 and a frequency of 300. I can plot this point here. To draw the graph, we simply join our points together like this. Part B says 100 students take more than k minutes to travel to college. Use your graph to estimate the value of k. K minutes. K is our time. 120 students take more than k minutes. So in order to find k, we first need to decide how many students we're working with. We're looking at the top 120 students. So I can say 300 minus 120 gives me a cumulative frequency of 180. This is the value I need to find on my graph. So let's put in my graph. And I can see that 180 will sit over here between 160 and 200. To find k, the amount of minutes, draw a line from 180 horizontally to the graph. Now from the graph, I can draw a straight line down to my x-axis to look for my time. And we can see this line touches the axis at 35. So as my answer, I can say that k is equal to 35. Part C says calculate estimates of the mean and standard deviation of the times taken to travel to college by the 300 students. Now, in order to calculate the estimate mean and the standard deviation, we need the midpoint of each interval and the frequency of each interval. So let's start with the midpoint. For our first interval, midpoint between 0 and 10, is 5. The second interval between 10 and 20 is 15. 20 and 30 is 25. 30 and 40 is 35. 40 and 60 is 50. 60 and 90 is 75. Now I can find the frequencies. To find the frequency of each interval from a cumulative frequency graph, all we do is subtract the cumulative frequency before the interval. So from our first interval, it will remain the same, 34. For our next interval, 86 minus 34 gives us 52. 142 minus 86 gives us 56. 208 minus 142 gives us 66. 265 minus 208 gives us 57. And 300 minus 265 gives us 35. Now we have the midpoints and the frequencies. So let's start with the estimated mean. To find the estimated mean, all we need to do is multiply each midpoint by its respective frequency and add these together. So I can say the estimated mean is equal to 5 multiplied by 34 plus 15 multiplied by 52 plus 25 multiplied by 56 plus 35 multiplied by 66 plus 50 multiplied by 57 plus 75 multiplied by 35. And then we divide this sum by the total number of students, which in this case is 300. So now I'm going to take my calculator and I can say 5 multiplied by 34 plus 15 multiplied by 52 plus 25 multiplied by 56 plus 35 multiplied by 66 plus 50 multiplied by 57 plus 75 multiplied by 35. Divide by 300 is equal to 33,78. I'm going to round off to 3 significant figures and I get an estimated mean of 33,8. Now that I have my mean, I need to find the standard deviation. So let's make some space. To find the standard deviation, we say standard deviation is equal to EX squared minus EX squared, all under a square root. Now, EX squared with a square is outside of the bracket is the square of the mean. And we found that the mean is 33,8, which means EX squared is 33,8 squared. But we still need to find EX squared, where the square is inside the bracket. And to do this, we square each midpoint and we multiply it by the respective frequency. So I can say EX squared is equal to 5 squared multiplied by 34 plus 15 squared multiplied by 52 plus 25 squared multiplied by 56 plus 35 squared multiplied by 66 plus 50 squared multiplied by 57 plus 75 squared multiplied by 35. And again, we're going to divide the sum by 300. So I'm going to take my calculator. I'm going to say 5 squared multiplied by 34 plus 15 squared multiplied by 52 plus 25 squared multiplied by 56 plus 35 squared multiplied by 66 plus 50 squared multiplied by 57 plus 75 squared multiplied by 35. Let's divide this by 300 and I get 1559,25. I'm going to write this over here. 1559,25. Now that I have a value for EX squared and the square of the mean, I can find the standard deviation. So I'm going to make some space and make a note of EX squared up here. And now I can fill my values into the formula. So I can say standard deviation is equal to EX squared 1559,25 minus the square of the mean 33,8 squared, all under a square root. Now I can take my calculator, I can say the square root for 1559,25 minus the square of the mean 33,8 squared is equal to 20,415. Let's round off to one decimal place and I get a standard deviation of 20,4. Question 6a says find the number of ways in which the 10 letters in the word amalgamate can be arranged so that there is an M at the beginning, an M at the end, and no A's are together. It is always a good idea to make a note of your repeated letters. So in the word amalgamate, we have got 4 A's, 2, 3, 4. We have 2 M's. Then we have L, G, T, and E. The question tells us there's an M at the beginning and an M at the end. We have 2 repeated letters, so we don't need to account for the M's. The only thing we need to account for is that the A's are not together. We have got 4 A's and 4 other letters. I'm going to write them over here. L, G, T, and E. The only way that the 4 A's will not be together is if they sit between these letters. So in these spots over here. And we can use this to find the number of different arrangements. Arrangement matters, so we need to consider factorials. Let's start with L, G, T, and E. I've got 4 letters. So for my arrangement, I can say 4 factorial. Now for my A's, I have got 1, 2, 3, 4, 5 possible spots for 4 letters. Let's multiply this by 5C4. Let's take my calculator. And I can say 4 factorial multiplied by 5C4 is equal to 120. There are 120 arrangements. Part B says find the number of different ways in which the 10 letters in the word amalgamate can be arranged with exactly 3 letters between the 2 M's. So let's start with our M's. 3 letters between them. Let's put this into a bracket. I've got 5 in my bracket, so I need another 5 letters. In the word, I have 4 A's. I have 2 M's. And then I have L, G, T, and E. For the 2 M's, I have 2 double letters, so I don't need to account for these. Of my 8 remaining letters, I've got 8 spots for them. So for my arrangement, I can say 8 factorial. I have 4 repeated letters, so we need to divide by 4 factorial. But this bracket with the m's can sit over here, 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 or here. There are 6 possible spaces it can sit in. So I need to multiply by 6. Now I can take my calculator and I can say 8 factorial over 4 factorial multiplied by 6 is equal to 10,080. There are 10,080 possible arrangements. Part C says 5 letters are selected from the 10 letters in the word amalgamate. Find the number of different selections in which the 5 letters must include at least one M and at least 2 A's. We're working with selections, which means arrangement does not matter. We have 10 letters in the word amalgamate. We have 4 A's, we have 2 M's, and we have L, G, T, and E. The question says that of the 5 letters must include at least one M and at least 2 A's. So we could have 1 M, 2 A's, and 2 other letters. 1 M, perhaps we have 3 A's, and one more letter. We could have 1 M, and all 4 other letters are A's. We need at least 1 M, which means we could also have 2 M's. We could have 2 M's, 2 A's, and one more letter. We could have 2 M's and 3 A's. These are all of the selections that we need to consider. Because this is not an arrangement, we have accounted for the M's and we've accounted for the A's, because even if we have 4 A's and we're only using 2, if we swap one A for another, the selection will not change. We still have 2 A's. So now we don't have to account for A's and we don't have to account for M's. We only need to account for L, G, T, and E. We have 4 letters, and in our first option we have 2 spots. So we consider 4, C, 2. For our second option, 4 letters in 1 spot. So to account, we say 4, C, 1. For option 3, we have 1 M and 4 A's, but this is still an option we need to consider. This is one option. For our fourth option, we have 2 M's and 2 A's. We have 1 spot out of the 4 letters. We account 4, C, 1. For our fifth option, we already have all of our letters, but we need to count this as an option, as a selection. So this is also 1. When working with NCR, if your R value is 1, then NCR is equal to N. So 4C1 is equal to 4 over here and over here. Now all I need is the number of selections from 4C2. Take my calculator. 4C2 is equal to 6. So now I have 6 selections plus 4, which is 10, plus 1, which is 11, plus 4, which is 15, plus 1 is 16. So my answer is 16. Kestrels are birds whose adult wingspans are normally distributed with mean 74,8 centimeters and standard deviation 3,2 centimeters. A random sample of 120 adult kestrels is selected. Part A says how many of these 120 adult kestrels would you expect to have wingspans between 72,4 centimeters and 76,3 centimeters. To find the number of kestrels, we can multiply the probability by the total kestrels of 120. We're working with normal distribution. So to find our probability, we're going to use the formula Z is equal to X minus mu over standard deviation. Mu, the mean, is 74,8. Let's make a note of this. Mu is 74,8. And the standard deviation, sigma, is 3,2. The question is asking us to look at wingspans between 72,4 centimeters and 76,3 centimeters. I'm going to make a note. 72,4 centimeters is smaller than X, which is smaller than 76,3 centimeters. To find the probability the wingspans are between these values, we need to find the probability of the wingspan being smaller than 76,3, and then we subtract the probability of it being smaller than 72,4. So let's start with an X value of 76,3. I'm going to say that Z is equal to 76,3 minus mu 74,8 over standard deviation 3,2. Now I can take my calculator. I can say 76,3 minus 74,8 divided by 3,2 is equal to 0,46875. When finding a value for Z, round off to 3 decimal places. So in this case, Z is equal to 0,469. Now I can look at my distribution table. We have 0,4. 6 gives us 0,6772. I'm going to write this up here. 0,6772. Then we account for 9, so we add 32. So add 32, and this becomes 14,8. 0,6804. I'm going to put this over here. Probability of Z is equal to 0,6804. Now I want to find the probability that X is smaller than 72,4. So I can say Z is equal to 72,4 minus mu 74,8 over standard deviation 3,2. Take my calculator. 72,4 minus 74,8 divided by 3,2 is equal to negative 0,75. So I can say Z is equal to negative 0,75. But we cannot use a negative in our distribution table. So to find the probability, we're going to say probability is equal to 1 minus the probability that Z is positive 0,75. Now let's go to our table. We have 0,7 moving across under 5, 0,7734. So I can say the probability is now 1 minus 0,7734. Take my calculator. 1 minus 0,7734 is equal to 0,2266. Equal to 0,2266. To find the probability that X is greater than 72,4 but smaller than 76,3, we can subtract 0,2266 from 0,6804. So I'm going to say 0,6804 minus 0,2266 is equal to 0,4538. To find the number of adult kestrels, all we need to do now is multiply by 120. Let's say multiply by 120 is equal to 54,456. We're working with birds, so we round off to the nearest whole number. And as our answer, we have 54 kestrels. Part B says the masses of adult kestrels are normally distributed with mean mu kilograms and standard deviation sigma kilograms. It is known that 20% of adult kestrels have mass greater than 0,202 kilograms and 28% have a mass less than 0,15 kilograms. Find the values of mu and of sigma. We need to find two unknown variables, which means we need to use simultaneous equations. We're working with normal distribution, so we're going to use the formula Z is equal to X minus mu over standard deviation. We need to use this formula to create two equations. So let's look at the information. The question says that it is known that 20% of adult kestrels have a mass greater than 0,202 kilograms. This is an X value. I'm going to say that X is equal to 0,202. 20% have a greater mass. But remember that normal distribution always works with smaller than X. This means that 80% of adult kestrels have a mass smaller than X. So I can say my probability is going to be 80% as a decimal, 0,8. Now let's see what else we know. 28% have a mass less than 0,185. This is our other X value. So X is equal to 0,185. 28% have a mass less than, so our probability is equal to 0,28. We have probabilities, so we can use our normal distribution table to find values of Z. Let's start with the probability of 0,8. When finding a value for Z, we need to find the probabilities in the table that is closest to the one that we're looking for. We need 0,8, and the closest values are 0,995 and 0,8023. We always work with a smaller value. So in this case, 0,7995. For this probability, Z is 0,8, 4. So I'm going to write this over here, 0,84. But we don't want 0,995. We want 0,8. So we need to add 5 to this. And if we add 5, we need to add 2 to our Z score. So Z is 0,842. I'm going to make a note of this over here as well. Z is equal to 0,842. Our other probability is 0,28, but we know that a distribution table only starts at 0,5. If you have a probability smaller than 0,5, that shows us that our Z score is negative. So we need to convert it. So all we do is we can say the probability of negative Z is equal to 1 minus 0,28, and we get 0,72. We can find this value in our table. Let's find the closest probabilities. We're looking for 0,2, and it will sit somewhere over here. We always consider the smaller value, which in this case, 0,7190. For this probability, Z is 0,58, but remember it's negative. I'm going to say negative 0,58. But remember, we don't want 0,7190. We want 0,72. So we need to add 10 to this. And if we add 10, we add 3 to Z, and this becomes 583. So let's make a note, and I can say that Z is equal to negative 0,583. And now with these values, I can create my equations. So for a Z value of 0,842, I can say 0,842 is equal to x 0,202 minus mu over standard deviation sigma. We are solving for mu and for sigma. So let's multiply both sides by sigma, and I get 0,842 sigma is equal to 0,202 minus mu. Mu needs to be positive, so I need to move it to the left. I'm going to make some space, and I can say that mu is equal to 0,202 minus 0,842 sigma. This is our one equation. So let's find our other one. We have a Z value of negative 0,583. I can say negative 0,583 is equal to x 0,185 minus mu over sigma. Let's multiply sigma out. I'm going to get negative 0,583 multiplied by sigma is equal to 0,185 minus mu. Again, mu needs to be positive, so I'm going to make some space. And I can write my equation as mu is equal to 0,185 plus 0,583 sigma. Now the value of mu in this equation is the value of mu in this equation, which means that this equation is equal to this equation, and we can use this to find the value of sigma. I can say 0,202 minus 0,842 sigma is now equal to 0,185 plus 0,583 sigma. Let's put like terms on the same side of the equal sign. So on the left, I'm going to have 0,202 minus 0,185 is equal to 0,583 sigma plus 0,842 sigma. Now I can take my calculator. 0,202 minus 0,185 is equal to 0,017. 0,017 is equal to, on the right, I have 0,583 plus 0,842 is equal to 1,425. So I get 1,425 sigma. Now to find sigma, I can divide both sides by 1,425. And I can say 0,017 divided by 1,425 is equal to 0,0119. 0,0119 is my value for the standard deviation sigma. With this, I can now find mu, and I'm going to substitute it into this equation over here. So I can say that mu is equal to 0,202 minus 0,842 multiplied by 0,0119. Take my calculator. 0,202 minus 0,842 multiplied by 0,0119 is equal to 0,1919 which gives me a mu value of 0,192. Part C says 10 adult kestrels are selected at random. Find the probability that fewer than 3 have masses greater than 0,202. We're looking at fewer than 3 birds. So we're working with either binomial or geometric distribution. We have a total of 10 adults. So we are working with binomial. When we work with binomial distribution, we use the formula NCR multiplied by P with an exponent of R multiplied by Q with an exponent of N minus R. We're working with 10 birds, so N is 10. The question tells us that we are looking at the masses greater than 0,202, and from part B, we saw that 20% of these birds have a mass greater than 0,202. This means that our probability P is equal to 0,2 and Q is equal to 0,8. The question wants us to find the probability that fewer than 3 of these birds have masses greater than X. Fewer than 3. So if we're looking at X values smaller than 3, we have to consider X values of 0, of 1, and of 2. These take on the R value, our restrictions. So let's start when R is 0. NCR becomes 10C0 multiplied by P 0,2 with an exponent of R, which is 0, multiplied by 0,8 with an exponent of N minus R, which is 10, plus 10C1 multiplied by 0,2 with an exponent of 1 multiplied by Q 0,8 with an exponent of 9 plus 10C2 multiplied by 0,2 with an exponent of 2 multiplied by 0,8 with an exponent of 8. Now you can put all of this straight into your calculator, but before we do that, let's just tidy it up a little bit. When working with NCR, if your R value is 0, then NCR is 1. We also know that any value with an exponent of 0 is 1. So now we have 1 multiplied by 1 multiplied by 0,8 with an exponent of 10. So we have 0,8 with an exponent of 10 plus NCR. If R is 1, then NCR is 10. So now we have 10 multiplied by 0,2 multiplied by 0,8 with an exponent of 9 plus 10C2 multiplied by 0,2 squared multiplied by 0,8 with an exponent of 8. Now I can put this into my calculator. I've got 0,8 with an exponent of 10 plus 10 multiplied by 0,2 multiplied by 0,8 with an exponent of 9 plus NCR 10C2 multiplied by 0,2 squared multiplied by 0,8 with an exponent of 8 is equal to 0,6777. Round off to 3 significant figures, and I get an answer of 0,678.